Hello, y'all. Darrell Lee Berry Jr. here, back with some more physics and uh, technically some astronomy as well. It'll lead into some astronomy stuff later as we go a bit farther, like the stuff that we're working on now. What I plan on doing today is actually going through some homework solutions. Homework 1 didn't do too well on. Got the solutions though from the professor, so we could review it for our pending exam. So what I plan to do is go through those, see what I did wrong with the homework problems, and see about improving that for the exam. So I have everything set up. And keep in mind, I do offer tutoring on physics, math, and astronomy, undergraduate level tutoring, or GED, or if you're just interested in science, you could let me know. You can hit me up. If you're in the Dallas, Texas area, we can set something up in person. Otherwise, we can set something up online, like through Discord. My Discord link is linked in the upper right corner. And we'll go ahead and get started. So we're using Goldman's. And the first problem is problem 7 here. So this is number 7 in Goldstein. So it says, show that Lagrange's equation in the form of equations 1.53 can also be written like that. And if I remember right, the equation 1.53 is the standard Lagrange equation, which is going to be, for instance, dx of partial the Lagrangian over partial q derivative minus partial the Lagrangian over partial q, and that all equals 0. So it seems to be saying that this equation can be written in the other way successfully. These are sometimes known as the Nielsen form of the Lagrange equations. Notice there's a q on the other side. So let's see what we have here, and let's go through the official way of solving this. So the first thing I notice is that so instead of this being 0, I mean, in the default case that we do it, it's equal to 0. It's not always. We'll go later into the constraint equations and how they can be, what's the word? Multipliers. I'm not sure we'll get to that today, but we'll try. So basically, we have to put the equation on the left into the equation on the right. So the first step that she suggests is to write out the solution. And she's really a good professor. She takes time to help us out. I have some good explanations. So this is my first time going through her solutions. I'm sure they'll be fine. We'll take a look and see. And if you're watching, be sure to drop a line. Let me know you're there. Well, I see somebody's there, but drop a line. Let me know who you are. Let me know if you have any questions as well, any comments. I'll be glad to try to respond to you live. And so we'll keep on going. So the first thing she suggests is to write this out. Write the solution out. When I say the solution, this is what we're trying to get to. So T dot, T should be the kinetic energy equals dt over dt. as far as the kinetic energy. And as it looks like this is being equated to the entire equation on the right. Oh, I see. So what she's doing is actually taking the derivative of this. So T dot equals the full derivative with respect to T. And T must be in terms of Q dot Q and P. So we know the Lagrangian is like this. So it seems that T must also be in this form. So this equals partial T respect to partial Q dot and d Q dot over dt plus partial T partial Q and dq over dt plus partial T to partial T and then dt over dt. Of course, this equals 1. So this cancels. So we're left with what the solution has, which is this. Also notice there's a summation on it. So and the dq dt, or the dot on it, ends up being q double dot plus this up being q single dot. So we have this. And as the derivative showed, this is the chain rule for this. So let's see. So what we did here, like this entire thing, is this. So that means that this entire thing has to get a derivative with respect to q dot. So we have partial T dot over partial Q dot J equals partial Q dot J of all of this, which I'll just copy down. And see what happens here. So it seems that The first thing we can do is simply distribute it. So I can basically distribute this partial derivative to everything up inside. And I distribute this, we have, and it looks like the summation stays. So we have the summation I of partial squared over partial q. This is the left side I'm writing first. So I'll keep everything on the same side, j, and partial q dot. And these should all still have a j. So I left these j's off. And did I leave them up there? So I'll put these. So not only is it accurate, but notation actually helps me keep track of everything by keeping the notation correct. And this will still be a D. I still have the Q dot at the end. This will be plus partial squared T still over partial Q dot J, and still a partial QJ. This will have a Q dot J plus partial squared T over partial Q still dot J and partial T. So if I'm looking at this correctly, going back to the solutions, that looks like I have it correct. I do notice another detail. I just noticed that the potential, the kinetic energy is actually summed over I. This seems to be an important detail. So all of these are actually I's. And why would that be the case? I suppose because the Q's are J's from the initial equation. So these are actually J's. And the T in the original equation, if we look at the problem in the book there, doesn't have any indices at all. So we're taking the derivative of T, which has these coordinates, but it has no indices of its own before we take the derivative over the coordinates. So it seems that's why it gets its own set of indices. So Q still has J. Excuse me, the Q under the Lagrangian still has J, but the Q under T has I, is what I'm seeing. So Q, T. So one of these is going to have, so if I keep the same pattern that I had before, the one on the right side is the kinetic energy. So it seems to be correct, except all of these will be under I. Right. It seems to be good. So the kinetic energy, which is being um, added its unique indices, since they didn't have indices before, on the I, which is this, which is all of these, and thus the partials that relate to the kinetic energy still have their eyes. The one from the original equation here still has their J's, and the squared at the top. I mean, it's just a d squared, so it doesn't matter. So let's see. I notice that there's a fourth term. So the first term in mine matches. This term matches. That term, I think, matches. Oh, that's why I forgot to do the chain rule on this part here. So this is chain rule. These. So I also have plus. See if I can write this the same way. I. That's correct. We have some I partial over partial Q J Q double dot. This is I plus some I partial Q J because it's coming from the initial one dot. And we have Q dot J, which is this one here. So that will be all the terms. And have to keep in mind that the first part of these is just a constant, so it stays there. So this one, the wrong one. This one is with the Q double dot one. And this one is with the single Q dot one. So I believe that is now all the terms. So here I can write this better as this is one chain rule, and these are another, and this one did not have a um, a term that followed it. That looks good so far. So another thing she did was, so the ones that's squared is the derivative of t. The ones that's not squared is the derivative of the multiple here. So I noticed that she has d or dq dot, q double dot is 0, and that makes sense. So this one is 0 because that's the same thing as d dt of 5. It's going to be 0. Q double dot is a constant with respect to q dot. And this one, the one thing I messed up on here is this one still has an I, and this one is 0. Oh, okay. So this equals not 0. If and only if I equals j. So this is literally, maybe I should write this in blue as well. This is partial qj. Oh, it's partial q I dot over partial q j dot. So if they're different, then it's just like this. If they're the same, I guess it equals 1. Just like dt equal to 1. I'm not sure about that though. Here, like it should equal 1. The same thing over the same thing. All right, so let's see what the next line says. So we have partial t dot over partial q dot j equals, so we still have some I partial square t over partial q j dot partial q I dot and q double dot, the first term, plus sum over, I know that she didn't write which is summing over, but I'm pretty sure it's still I partial square t over partial q dot j partial q I is Q I dot. So that's the next term I have there. That stays. Then we have plus partial squared T over partial Q J dot partial T. That's the next term I have. The next one is 0. And the last term is only going to equal not 0 if I equals J. So I can take away the summation. I'm summing through I. So I can just write this whole thing as J and say hold up. I'm looking at this term here. What detail did I miss? The Q dot terms. Oh, she did make it the same. So if I equals J on this last term here, then this is going to be some. This is going to be so basically I'm summing through I until it equals J. So now it's just only J's. So it's partial Q dot J over partial Q dot J, summed over I until they equal J, then T over T Q J. So now this is going to equal 1. I have exactly what she has, which is some squared T over partial Q dot J partial Q dot I Q Q dot dot I plus some I partial squared T over partial Q dot J partial Q J q dot I plus partial t over partial qj. I'll put this term first so it matches these solutions, plus partial squared t over partial q dot j partial t. All right, so we have that. Then it looks like she subtracts one side. So I'm going to subtract this. Then it equals the sum over these two, sum together. Then plus last term. Let's see if I can put it on the same line. And I noticed she broke the term apart. So we end up having uh, partial over partial t, partial t over partial q uh, dot j. That looks like she points out that all of that is d of dt over partial t over partial q dot j. I'm seeing that correctly. I do not think I want to try to work that out. We did partial derivative of t, or at least we did a time derivative of t. So how easy it is to show that. The solutions are saying that this is d dt of partial t over partial q dot j. So this, we know that t has the 3 coordinates. Does not seem straightforward how that's the case. I suppose if I put the dt on the t, I was thinking of putting the d of dt on the t, so I get dt t dot again, which will give us back what we had here. I guess simply because original Lagrangian with these coordinates, the dt, so it might have made it clearer if I use the proper term here as a d of dt. Interesting. So in this case, basically potential energy is the Lagrangian, if I'm understanding this correctly. And copy this down. This equals this. I can plug it in. So then I have partial t dot q dot j minus partial t over partial q j minus partial t over partial q j equals qj. So that's partial t dot over partial q dot j minus 2 partial t over partial qj equals qj. That's what we wanted to prove from the start. So I guess the only challenge is understanding how I can tell that this that equals. The question I would say we have. the code. That out for if those things can be swapped easily. So I think I shall try that. See what we get. Let's see if this actually equals that first thing. So by replacing this first thing with this and one of these, then we get the answer that we need. So we have d dt of partial t over partial q dot j. So in t is a function of q dot I, q I, and t. We have d of dt of partial t over partial q dot I. I'm not remembering if all of these are I. The thing that we're taking the derivative of goes last, and the terms of the variables of the term go first. So we have partial qi, partial t, partial qi, partial qi, partial q dot j plus partial t, partial qi, partial qi over partial q dot j plus partial t, partial t. I believe this should be a full-time derivative. dt over dq j dot. All right, so we have this. Then we have to take the time derivative of this, and we may already be close to seeing how it matches, but let's be sure. So this equals partial square t over partial t partial q dot I partial q I over partial q dot j plus partial t over partial q dot I partial squared q I over partial t. I'm getting just the first term over partial q dot j. Let's see if this looks familiar. Like all of these should be zero. Trying to use the ask her about this derivative, or I might have it in my when I first did it the first time, but I won't scroll through. But I may come back and do this another time. But we have that. So if I was to say in a shortcut, first write out the solution. Two, find difference needed. Three, plug. So I guess at this point I would say assume that what you get when you pull out the difference needed, which is one of the partial t's and one of the thing that we're going to double here. I mean, I guess it's fair to assume it's equal without a better solution, but I might need to ask about that derivative. All right, let's go to problem 2. And this one is 1.8. So it's the same problem. Next page. Bottom of this one, next one. If L is a Lagrangian for a system of n degrees of freedom, satisfying Lagrange's equations, show by direct substitution. So with L is a Lagrangian, n degrees of freedom, satisfying Lagrange's equations, show by direct substitution that L prime equals L plus df over so many variables also satisfies the Lagrangian equation. The order of Lagrange for short. F is any arbitrary but differentiable function of its arguments. Right. So let's see what we have for this one. So we know that the Lagrangian function is d over dt partial L over partial Q dot minus partial L partial Q equals Qj. And f is a differentiable function. So the first thing she did was make f differentiable. So df over dt equals the sum I partial f over partial q, and why don't we do it this way? It'll be partial f over partial q1 and full derivative q1 over dt plus all the way down to partial f over partial qn, the q1 over qn over dt plus partial f over partial t dt over dt, which will equal 1. So we have the sum I of partial f over partial q I d qi over dt plus partial f over partial t. So that equals sum over I partial f over partial qi dot plus partial f over partial t. So that defines that function as differentiable. And then we have, okay, so I've made this function differentiable. And that's why she did that, because it's listed that way there. So I guess the first thing is still the same thing we did last time, write the solution. Difference needed. So L prime equals L plus this. So we have to actually get the differentiable function in the proper form. And now we'll actually plug this into the early Lagrange. Uj might be equal 0. So we have dt partial over partial qj dot of this for this first term. So this equals d dt of so it's partial L q dot this equals L plus F. It's L plus the F over dt. Oh, hey, Wilfredo. How you doing? You're welcome. Thanks for dropping a line. Glad you're enjoying. I'm not a professor yet. I am a TA, but I look forward to being a professor in the future. Now let me know if you have any questions. Hopefully you find it entertaining and informational. And basically what we're doing is trying to work through these solutions that professor has. And I see how she basically plugged in this as a full derivative here. And now we're going to plug this into the Euler-Lagrange formula. But it seems to be some detail that's unclear here. We have partial L prime. So why don't we look at the problem again in the book here. So you see right here it lists on the very top line, it lists L prime is L plus the derivative f of dt. So it seems that I'm going to plug this into the Euler-Lagrange, the first part. I guess that was just shorthand. So why don't we say that this is so I'll write this here and say d dt partial over partial qj dot of L plus, let's just call this f prime because this is the derivative of f, and L prime is L plus the derivative of f. And on the second line, we plug those things in. And on the third line, we have partial L over partial Q dot J plus partial L over partial partial F prime over partial Q dot J. So there seems to be a direct substitution of that right there. Now, one of the things that she mentioned, looking at this, because this sums over an infinite, potentially near infinite or infinite number of coordinates, which means that if you notice here, I wrote this out as 1, and this is 2, 3, 4, 5, whatever. and it goes all the way up to n, and thus I consolidated this into this summation over I. So that means that this will be a summation over I, and the only way it'll actually have a value that's not 0 is if I equals j. So if I doesn't equal j, that means that this q here and the summation, they're not the same. And I can see how that will equal 0. So this equals not 0 if and only if I equals j in that summation. So we have that. And then we have the derivative of that, the time derivative of that. So I'll just distribute the time derivative equals d dt partial L over partial q dot j plus the dt partial f prime, and I'm summing over I, so I could just call all of this j over partial q dot j. And let's see what she does with this. So this left part stays the same, and so I'll just parentheses that down, plus, so I believe this part is the chain rule. So two parts to this. So see how that part stays the same. I'm seeing exactly what was done with the F part. So written down, it looks like this. Sum, which I assume is the sum of I partial squared of F over partial Q by partial Q J, and then Q dot, that seems to be an I, plus sum, which I'm assuming is over I partial squared F over partial Q by partial T. So if I were to extrapolate that out, it seems like it would be applied to this, the d of dt of that. Now, I could see it on the second part. So the second part is clearly this. You have df of dt. And here now we have the square of that. And actually, hold up. I need to ask her about this mass. Q dot J F Q dot D of dt D prime D of dt L F. Okay. I can have a better understanding of what's going on. So I has to equal J for this part to not equal 0. So I think I need to ask about this part. This part of the derivation. Plug it into Lagrangians. It's like everything that is the extra F cancels. Oh, I see what I'm doing wrong. F is only a function of Q, J, and T. So this is very important. there's no q dot. Right. So q I c. I think this is the detail list. I was thinking it was also of q dot. That will explain it. All right. Need to back up on this part. So I was thinking about it incorrectly. Find the difference. So we have L is of q dot j q j t, and F is of q and t. That's how you defined it. There's no dot. There's just a bunch of q's with no dots. You see that in the first line, partial t of the q and q dot by t. And then the F part, there's no double dot because there's no q dot in F. So if I plug this into so I'll do this piece by piece. Partial L prime or partial q dot j equals partial q dot j of L plus F prime. So this equals partial L over partial q dot j plus partial over partial q dot j of F prime equals, I'll bring this down, plus partial over partial q dot j of some I partial f over partial q I dot plus partial q dot j of partial f over partial t. So this seems like it should be 0 since there's no q dot dependence. This equals 0. And this will give us a chain rule. So this is partial L over partial Q dot J plus sum I partial squared f over partial q dot j partial qj q dot I plus sum I partial f over partial q I partial q dot I partial q dot j. And you'll know that there, this should still be 0. And this should equal partial L over partial Q dot J plus this equals not 0 when I equals J plus, so if I sums 2, so that equals J, that means that equals 1. We have partial F over partial J because we summed through and got J. All right. So realizing that uh, the function is only has the uh, coordinates Q and T, simplifies that. And now this matches what's in the book. So she got it. Yeah. Right. Oh, and this is a Q. Right. So now we have to the dt partial L prime over partial Q dot J. So that equals d dt partial L over partial Q dot J plus d dt partial F over partial Q J. So this was just copied down since this is the original form that we were looking for. And now we just have this. So see the squared. What they're doing is they're swapping these J, D, dt, F. So this equals, it stays there, plus partial Q, J, partial F over partial Q j partial q j over partial t plus partial over q j t t t t over d t. Right? This equals the same thing. d dt partial L over partial Q dot J So looking at the solution here, partial squared F over partial QJ is partial QI partial QJ. Q is right here is QJ, so QI dot plus, she still has a sum here. So since this one was going to be equal to 0 if we didn't take the sum, we remove the sum. But here we still have the sum, so we still have the ij going on. Q plus, this is going to be 1. So we have partial squared f over partial q j partial t. All right. And I guess this is still summing over j, or maybe both. Now I just need to get the second part, partial L prime over partial qj equals partial q. Oh, partial L over partial qj plus partial over partial qj, and I'll end in a bit. The battery's about to die, and I'm getting sleepy. So I think it's all adding up to a good time to stop in a bit. And this is actually f prime. Go out the notation. F prime, f prime. So it looks like she did swap that. Prime equals, I take this down, plus partial or partial qj of some I. Copy this down. Plus partial over partial qj of this. Look at that. So this equals partial L over partial qj plus, we see this seems to be the same thing as before. Sum of partial squared f over partial qj partial qi q dot I plus partial squared f over partial qj partial t. This looks legit. So we know that the equation is going to be this. So we know what our what do you call it? Substitutions. This is going to equal this minus this. And you can see that these things here are the same. So the extra stuff cancels. We end up with the original Euler-Lagrange equation, a partial L over partial Q dot J minus partial L over partial Q J. And we've proven that they're the same. All right. So hopefully that was entertaining, informational, and I guess we learned to make sure to recognize what forces, what I should say, coordinates are part of the functions that we're working with. Got a better understanding of partial derivatives, problem one and problem two. And what I'll probably do is come back tomorrow and continue working through this homework assignment. So I had several problems actually. So these were mostly the deriving problems, and the future ones will be the problems. We'll be solving stuff. So come back tomorrow evening and look for that. Might be a little bit later. Looks like I went I started at 8, went to 9:30. So I'll try to start at 8 again, but it might be a bit later, depending on what the environment is. I'm in a shared environment now, so we'll see. Thank you all for popping up and watching. Hopefully you like and subscribe if you haven't. Help me get to 1,000 subscribers. Let me know in the post things you'd like me to work on, or in the comments of the video. If you have any undergraduate things you'd like me to solve or have questions about, let me know. I'd be open to do a problem or two. And hope you have a good one.